All right. Hello, everybody. I'm EVM from APL, and thanks for coming out to the talk here. I'm going to talk about some research we're doing at APL on reverse engineering, mainly static analysis, static binary analysis, and trying to speed up the process, help out analysts so we can understand binaries, do vulnerability analysis faster. So what I'm talking about today, I'm going to talk to you a little bit about kind of some high level stuff that we're doing, kind of the long-term research that we want to do. And I'm also going to talk about a technique that I developed for slicing up a binary into pieces. And so that's kind of the Cutlass thing. See, it's a joke, haha. Thanks. So the motivation behind this is, I'm guessing the folks in the room, I'm guessing you guys have done reverse engineering, or you've got some interest, or you're at least familiar with it, with the subject. But, if you're not, a lot of what we do in InfoSec is built on top of reverse engineering, right? When we have, we have new malware samples, they get detected in some way. A lot of that is built on humans tearing apart malware binaries, or if it's on the other side, if it's, sort of the red team side, there's people doing vulnerability analysis are pulling apart binaries, reverse engineering binaries in order to figure out how devices work and then find vulnerabilities, attack them, right? The problem for me is that RE is very manually intensive. There's a lot of domain expertise that's involved. And particularly where I work is in embedded systems. So, what happens in my day job is the government comes to APL and they say, a lot of times it's it's a military organization like the Navy, and they'll say, hey, we want to put this, we're going to retrofit this system on a submarine or plane or whatever, and we want to put this box that we bought from Best Buy, and we want to stick it here in the, in the ship, and so our job is to say, you want to do what? Okay, hold on. Okay, here's why that's a bad idea, or here's the vulnerabilities that exist, and here's ways to, mitigate them. Here's a way to design the system so that, those vulnerabilities can't be exploited. So I spend a lot of time in embedded systems, reversing them, pulling them apart. If you're not familiar with embedded systems, they, when you're reversing, or looking at, Linux or Windows code, you get a lot of things that you don't have to look at. You don't have to dig into. You don't have to dig into the kernel. You don't have to dig into the system libraries. Those are all kind of well understood. You get those whenever you're calling into a system library. That's well labeled, right? In embedded systems, especially, so this is like in the RTOS world where you have like you might have a single large binary that is, it's got the application binary, the operating system, and libraries all smashed into one program space. So what happens is all of that gets compiled and linked together, and if there's no symbols, then you don't get any symbol information. So what you get is something that looks like that on the bottom left. This is nasty, or if you drop it into IDA and you get, okay, I've got 12,000 functions, and IDA doesn't recognize any of them. I get this big nasty, call graph, just super complicated, call graph, and I've got to, make some sense of it. So we spend a lot of time just kind of churning through, binaries that look like this. And so my whole motivation is to make that process faster, both for me and people like me, but also for newer folks. We want to make binary reverse engineering just more accessible, more tools available so people can kind of pick it up quicker and get up to speed quicker. So I'm going to talk about it a little bit more, but the previous research in RE has mainly focused, so the main academic problems that are being researched and solved are code-to-code translation, so like decompilation, right? People are pretty familiar with disassembly. Ghidra just came out, so Ghidra has a built-in decompiler that's based off of P code. Hexrays, of course, they've had their decompiler that's out for a while. Generally, the way these works is you take the binary and you translate it to some intermediate language, sometimes even a higher level language, and you take the binary, convert it to some intermediate language, and then that gets converted to a high level language like C, right? That's your basic kind of decompilation steps. And then the other part is function level matching. So things like bindiff, diaphora that are out there. Ghidra, of course, has the version tracker tool that lets you take two binaries and match functions between them. That's mainly where the research in speeding up static analysis has focused. And those problems are pretty well solved. So I'm going to talk a little bit about just thoughts about automated reverse engineering and how we can make that better, and other areas that kind of need to be explored. So I mentioned the so I'm gonna talk a little bit more about function matching and decompilation, but it seems to me that when we reverse engineer code, reverse engineers are operating on at least 4 levels, and most of the research isn't really taking that into account. The people that are trying to work on machine learning and deep learning approaches for software reverse engineering aren't really taking the sort of hierarchical abstraction of reverse engineering code, or the fact that there's hierarchical abstraction in the code into account. So in general, we kind of work. If you want to call this a stack, we're working up the stack to sort of try to understand at a higher level what the code is doing, right? So we're staring at, disassembly down here, right? Maybe, staring at disassembly down here. Maybe we've got a decompiler that brings us up here. We're trying to understand, we spend a lot of time just trying to label functions, understand, what the subroutines, what the functions are doing. And then usually we take sets of functions and then we group those into, into say like a library or just, a grouping of functions. So if you're doing malware, you look at, okay, here's the protocol section of the malware. Here's the, here's the part that launches a payload, and here's the part that parses the configuration or something like that, and those are all within the binary. So we tend to, as we're reversing things, we tend to move up and down that stack, right? So we're trying to kind of answer that higher level question. So we're tending to kind of answer that higher level question at the top, but we kind of, we kind of bounce around to sort of work our way upwards, right? We try to kind of zoom in on maybe the call stack that we care about, and so we'll go all the way down to staring at, opcodes to figure those things, to figure out a particular function. But we're generally trying to sort of work our way up to the top level where we can explain to somebody else what this code does. So as I mentioned, the current state of practice in RE is kind of like, looks kind of like this. We've got decompilation that kind of helps you go up to, takes your disassembly and translates it into a high level language like C. The problem with that is, there's no problem with that, but what you don't get out of that is you don't get you don't get C source that's labeled with function names and variable names, right? You get, sort of this blank C source with these abstract var1, var2 variable names. So it's good to have decompilation, and maybe it's easier to read C code, but it doesn't necessarily tell you anything about the functionality of that C code. You have to sort of interpret that for yourself. Function matching is also kind of going up here. If you have functions that you've seen before, those tools will help you match those, up at that level, which is helpful. But that actually doesn't do anything for, our current function matching approaches don't do anything to interpret or tell you about the functionality of new code. They just help you kind of match against code that you've seen before. So in general, what we are kind of the summary of what we want to work on at APL is techniques to build on decompilation and function matching, but to treat this as a problem where we're translating code back to natural language. So for most of us, that's English, right? We want to be able to have techniques that translate, whether it's binary or functions, libraries. We want to be able to tell an analyst. We want to have tools that we can run that will tell an analyst in your natural language, what do I think this function is? What do I think this set of functions are? We want to treat this like a natural language translation problem, building off of the kind of the existing research that's out there. I'm gonna talk a little bit. The rest of this talk is about something I developed that is really sort of up here. It's the idea of trying to group functions and group sets of related functions and determine what the object files or the libraries are, the static libraries within your binary. Because I think that was sort of a piece of the puzzle that I saw kind of a quick answer to. And I'm also going to talk about later on. I'm going to talk about kind of a data set that we're building to try to fill in more pieces of this, sort of more pieces of the puzzle, build more parts of the system. The thing that I like to relate it to Jarvis. If you guys have seen the Iron Man movies, right? Like Jarvis is this like sort of AI assistant for Tony Stark in mechanical engineering, right? And he says, hey, Jarvis, he can ask it some question about chemistry or physics or something, and Jarvis sort of spits it out, right? Imagine if we had sort of like a Jarvis for binaries, right? Where we had an AI that could say, this looks like networking code. This looks like crypto code. That's kind of the long-term thing that we'd like to build. Okay, so let me talk a little bit about CodeCut. And feel free to, this is a pretty small room. Feel free to shout out questions if you have them as we're going. Does anybody have questions on that section of it? Okay, cool. Yeah, feel free to raise your hand if you have a question. So the problem I decided to tackle, I call it the code cut problem. And so if you're familiar with languages like C and C++ that get compiled down to a binary that runs on the processor, you're probably familiar with this, at least in theory, with this with these steps, right? So you write your code and you write it in a bunch of different C files. This is just sort of generally the way that developers, they kind of segment their C files into, or their code functionality into different C files. and they compile it into object files, and then your linker builds that all into a binary program. Now, sometimes if you're dealing with malware or something like that, you get other things, you get packers and you get obfuscation. I generally don't deal with that kind of stuff. I think this stuff still applies, but it would be sort of like after you kind of get rid of your, any obfuscation that was built on top of, on top of the binary. In the embedded world, most of the products that I'm trying to reverse engineer are commercial products, and the developers aren't really thinking about, they're not trying to obfuscate their code for reverse engineering. They're just trying to sort of put a product out there, right? So there isn't like, I'm not accounting for any kind of weird stuff you might, tricks you might do to prevent reverse engineering. This is kind of just straightforward stuff. So the idea of the code cut problem is we want to recover those original object files in the binary program. So what the linker does is the linker just takes those object files more or less and just squishes them, one after the other. It links links all the function calls together, and what you end up with in your binary program is more or less the object files that you passed into the linker, in order, and they just all kind of get stuck one after the other and squished together into that binary. So the idea of the code cut problem, it's real simple. It's just, can we find those original object file boundaries? The cool part about that is that it gives you a lot of information about when you look at object files. Usually, that's kind of the hierarchical design, sort of the abstract design that the programmers put in there. If you look at the relationships between those object files, you can actually sort of immediately, sort of recover design information about the software. So yeah, that's what we're trying to do here. So the concept I came up with is actually really dirt simple. So if you think about C, you've got your pound includes and your functions. And so the idea is, so let's just say for a second we eliminate external calls and we just look at the directionality of calls. So we look at at the direction of the relationships between functions in this file. It's sort of obvious when you think about it, is that at first any function calls within this file are going to be going in the positive direction, right? And then towards the end, function calls are going to be going in the negative direction. And if we also look at that's for a particular function, that's functions that it's calling. If we also look at the reverse thing, any functions that call a particular function, that same relationship is going to hold. It's going to be called by functions in the positive direction, and then that's going to switch over to the negative direction. Sounds kind of trivial actually, but the cool part is that you can to some extent detect these edges in code. So what we're looking for really is we're looking for a negative trend and a switch back to the positive direction, because that will start our new C file, our new object file. So that's sort of the whole thing. And so you can imagine the next C file is going to look, we're going to have, it's going to start again in the positive direction and then go to the negative direction. this is the sort of the mathematical formulation for what I call local function affinity. So it's a way to think of that is it's just the direction that a function is sort of being pulled towards other functions around it, right? So is it called by functions, or does it call functions more in the positive direction or the negative direction? You know, which way is it sort of being pulled? And what I use here, I use this term. I use a log term. If you're a physics person, you might think, you know, if this was like a force vector in physics, a lot of times you use like an inverse square thing as you know, so as you go further away from the object, you know, the force is less. I went for a logarithm instead because I don't think it matters too much. I think that inverse square is a little bit too aggressive, and so logarithm seems to work for right now. I'm going to talk a little bit later about this big data set that we're building to test some of the stuff out. So we should actually be able to get some good results on whether logarithm or inverse squares or some other thing is a better way to factor the pull on that function. But basically what we're saying is we're just taking all of the functions that call this function, or that function calls, those are the references, and we're taking the logarithm of that distance, multiplying by the sign, and then taking the average of that. I mentioned in the previous slide, so I kind of, if you were following closely there, I mentioned here we've got to eliminate external calls, and if you spend a lot of time in a disassembler, you probably are thinking, okay, like how do we eliminate external calls, because we don't have any sense of that in the binary. There, you can't really see whether this was an external call or not. You don't get to see like what's the pound includes. None of that information is there. So what I do here is I do a fixed threshold of 4K. So which is kind of a hacky way to get around that, but it's basically saying anything. So I know for a particular function, you know, if I assume that the maximum object size, so that's basically saying what the maximum object size is. If it's over that, I'm just gonna throw it out and say it's external. So there's room for improvement there. So I'm basically I'm taking everything that's, you know, further away than a certain size from that function and just looking at the functions, you know, within that boundary. I'm also looking for so I have to detect edges then. And the way I do that is I just look, the edge detection metric looks for a negative trend, and then a switch back to the positive turns out to be about a change of 2 with this score, and we call that an edge. We just kind of made that up. Seems to work. So this is for a particular binary that I was working on. This is on the bottom. This is kind of the full thing, and then there's a zoomed in view, and you can see that this kind of holds, kind of works well here. So here's a very nice example, and this was cool. This was a real binary that I was working on evaluating, and it had some assert statements in there. So with file name, you know, so with file names left in the calls to the assert function, and so we were able to kind of from those file names, we're kind of able to validate somewhat whether this was working correctly. So so the names at the top are from those assert statements, and the so that's where we got those names from, and we could see a pretty nice. So here's an example where we have a positive score, goes down to negative, switches back. This LTC is another one where we have a positive score, negative, switch back, pretty nice. Some of these other ones, oops. So, here's one that's kind of messy. Some of these, this is kind of interesting here, this P1. So this is like the main thread of the whole thing. And had a lot of different functions. So it's like this is on the x-axis is function number here. So it's 40 functions or something like that. And at first it was like, oh, is this really working? But what's cool about this is what it actually shows is that even though this was originally one file, they put a bunch of different kinds of functionality within that file. So it's actually showing you some boundaries between functionality within that original C file. So played around with it. It's kind of, this was kind of like the first thing that I got to run it on that seemed to really first thing I got to run it on in it, and it seemed to really validate the approach. Okay, so far this has been all kind of theoretical and mathy, right? But so if you're an analyst, okay, so what? Why do I care about this? And this is the real cool part right here. So once you find your object file boundaries, even if they're not perfect, they're close, right? Usually we work with call graphs, right? We if you're in IDA or Ghidra, you do one of these things where I take a function and I want all of the cross references, all the functions that eventually call this function, or I take you can use plugins and things to find just paths through from one function to another function or something like that. Sometimes you can find you find a main entry function, and I want all the functions that are called by this function, so I get this giant nasty call graph of the whole binary. So instead, if I can find those object file graphs, instead of that big nasty call graph binary, I can now just I can simplify it and graph whenever one of these objects calls another object, I make that an edge. So I sort of bring it up a level. So that's this guy. So each of these things that we detected, and at first we came up with these names came from just sort of looking at the binary. But I actually have in the code later some stuff that tries to come up with a name of the binary based on strings. But so the cool part, so you got this graph. This is essentially a automated software architecture graph, and you can immediately pick out some interesting relationships here that you wouldn't see in a call graph. The call graph on this thing is so complicated that it's really nasty. Just some things to point out here. So here's a configuration. This was a C++ configuration code. Read stuff out of a config file and set variables. So you can see, okay, the reason everybody's calling that is they all need to read some configuration and do something with it. Down here's an events thing. So this was just functionality to register for a timer or a callback. And so you can see them all calling that. And another interesting bit here, here's a whole bunch of code. So this ends up, let me back up here. This is from here to about here. So almost a quarter maybe of the binary. And we can see it right here, these modules that didn't have any strings. And you can see that actually there's one call here to one of these functions, but otherwise nobody calls these functions, this whole subgraph, except for this configuration file. So you can immediately say, well, if I understand kind of what the config this is doing, I don't have to look at any of this code. If I understand this interface, I can just sort of ignore all this stuff. And then I can ignore basically a quarter of the program that way. So that's just something cool that you can, you can do with this immediately. This runs with LFA. It runs automatically right away on your binary, and you get this call graph to look at. So pretty cool. Here are the results. So far, which I'm going to talk a little bit about this later. There isn't a lot of, we don't have a lot of ground truth data sets to run tests like this on. In order to really have a data set, you need source code and binary, and ideally for me, you'd have source code, binary, and then your intermediate compiler artifacts, like your actual .o files and your map files and your symbol files, and you keep that all together. We don't really have any data sets out there that have all those things in them. And so this was my first shot at doing something for that, which was coming up with, it's basically compiling on my own a bunch of different embedded firmwares. I started out with GNU Chess for some reason. I'm not sure why as an x86 target. The rest are sort of embedded firmwares. Just to make a data set to test this out on. This worked, this kind of, validates the approach. I had a longer explanation of how these scores are calculated. The idea is that gaps are sort of anywhere in the code that scores aren't calculated for. Underlap is just a term I made up for disjoint areas. So places where where we describe the object file and the actual object file, don't line up. So obviously a higher match score is better, and a lower underlap score is better. So we actually have pretty good, some of these, 90%, 85%. It's like, okay, that's pretty decent. Some of the things, so like the reason that the PX4 firmware scored low is that this gap number is high. So there's a lot of, like, there's actually in that firmware there are functions where the function itself, and this is just how it's written, is larger than 4K. So we threw it out. Here in some of these other ones are low. These two are low with a higher underlap score because whenever you have, so in C++, if you have getter and setter functions, they're basically functions that access, they live within a file, but they access global data and they're used by people outside that file. This tends to link those functions up with the previous file, especially if they're, 'cause they're usually at the top of the file and they're not directly called by things in the file. So that's kind of what that's kind of why, so GoodFet has those and GNU Chess has those. GNU chess is C++, and that's what makes a low score. So probably the takeaway from that was maybe we want to factor in global data references as kind of like a follow-on score. Any questions on that? I know it's kind of dry material. Yeah. I'm not sure. Well, what do you mean if? Mm-hmm. Yeah. Okay. So for the camera, so the question is, yeah, basically, I guess, how did I compare or how did I come up with a before and after, or did I base it on binary and symbols, or how did I do that? Yeah. So for the GoodFet, yeah. So you can download the source. Actually, so all of these are open source, and so the way we did that is we took the source, built the binary. In the process of building the binary, got the map file. So that's the ground truth map file, right? And then we run our code on the binary without the benefit of the map file. So basically, our code tries to guess a map file is essentially, and so then we just compare two map files. So that's sort of how it's done. Okay. So this is a new algorithm that I came up with that I haven't added to the LFA code. So I'm going to talk about it later, but all of the LFA code is on GitHub. You can download it. It works as an IDA plugin. I'm hopefully going to be porting it over to Ghidra now that Ghidra is out there. Hopefully, maybe this summer, and hopefully we'll get this in there too. So we had played around with graph algorithms for a while. Graph algorithms are cool, but they tend to be computationally intensive. And we tried a bunch of different things, and they were generally very slow and didn't work really well. So I tried to come up with an algorithm to possibly beat LFA, and so this is what I came up with. The idea, this is really simple, and the idea is we still want to keep we want to do a graph segmentation algorithm, but a lot of times when you do that, you don't keep track of how those functions, the nodes in the graph, how they are organized in the binary. So a lot of times when you generate this graph, instead of saying, okay, I know these things are all organized in this linear direction, it turns into a sort of two-dimensional graph, and the algorithms try to segment that thing without really taking into account that original organization. So what I try to do is develop a, normally in graphs you're doing like a minimum. You're trying to minimize a score. And you make a cut based on a minimum score. This is a maximum cut approach. And the idea is, so if I look at all of the calls between functions here, and I take their average, so for a particular cut location, take this here. I'm looking at all of the calls that cross this edge. Okay, and I'm taking their distance and then averaging that distance. It's actually really, really, really simple. And what that's giving you is it's giving you a there we go. It's giving you an idea of where you might have a gap between relationships. So you can see I don't really have everything that's transiting here, and you can kind of visually see that in this picture. This is just sort of a made up example, but like I have related stuff here, I have a related stuff here, but anywhere where I don't have anything here, and most of the calls transiting this edge are big, then okay, maybe there's a gap in functionality here. And so we basically just calculate that score, take the maximum score, make a cut here, and then we remove these edges and run the algorithm again on this subgraph and this subgraph, and we recurse until we've cut it up, to whatever threshold. We basically just have to pick a threshold of size and then say we're not going to cut anymore. That's all I had on that. So this actually, I think this might actually work better than LFA. It's gonna be a little bit more computationally intensive. So LFA runs in if you're a big CS person, runs in order n, with n being your number of functions. This runs in n log n, so it's better than n squared, but it's going to be, it's still going to be more computationally intensive, but might end up giving you better results. So what's next? What are we going to do? I mentioned I need to implement max cut, and I'm hoping to. So a couple of people are working on Ghidra and IDA interoperability layers, which would be great. So I'm kind of hoping to wait for one of those to win out and then port my code to that, so you'll be able to run it on Ghidra and IDA. I'd love to build a nice, respectable GUI for it. One of the things, so I mentioned the guessing the name of the object file. One of the things we've got in there now is we've got the ability to guess the object file name based on common string references. So we got some simple code that just goes through all of your strings within that object file and says what are the common words, what are the common doublets, triplets, and then says here's a guess at what this object file is. And so if you have a lot of like debug prints, it actually works pretty well. So right now though you kind of you get some script output and you can then run those scripts on your thing, but you don't get to really interact with it. So it'd be nice to build a GUI to do that. And so I'd also like to get it tested more on this project I'm working on called All-Star. So as I mentioned, we don't have a great data set out there. In fact, there's no real data set out there. And you talk to folks in the community, everybody kind of acknowledges that this is a problem. It's people kind of have made some small data sets for their own research, but if you can imagine, pretty much any other field where machine learning or deep learning has been applied, there's usually some shared large data sets that everybody can kind of do their research on, compare notes and all that kind of stuff. So the next thing I'm working on is what we're calling All-Star, which is basically just like in one phrase, it's build all the things. So we're taking Debian Linux, which has about 30,000 packages in it, and we're going to build it for so theoretically with Debian, this is definitely theoretically in quotes, you can compile all those packages for all of the architectures that Debian supports. So you can compile it for x86, ARM, MIPS, PPC, and IBM S390. And so the idea is build all of those packages for all of those architectures, save all your compiler artifacts, save header files, shared libraries, and get as much as you can through the compile process. So get your RTL from GCC, get Gimple, which is GCC's like sort of high level representation. And so we actually have right now we have a working prototype. So it extends the DocCross project, which is basically a set of Docker containers that have cross compilers, and we just extended that to be able to build Debian packages, and it kind of works. That's like that should be my tagline, is like it kind of works. And so we've got in about 3 days. So this was running it on a single core. Obviously, this is going to need to get run kind of massively in parallel. But I needed to kind of walk before I ran with it. In 1 weekend, I was able to build 550 packages, and out of that, we got about 80 binaries that built for all 5 architectures. So that's where the theoretically Debian builds for those architectures, is that the packages, a lot of time, like every package will build for 64-bit x86 every time, but a lot of times they don't really. They're supposed to, they're supposed to look at your compiler variables and other config stuff, and in order to figure out what architecture to build for, and a lot of times they don't. So if that holds up, we could expect to get about 4,000 binaries, which would be pretty decent. If I'm hoping to be able to figure out some bugs, and maybe we'll get maybe we'll get a little bit more. If we could get, say, 8 or 10,000 that out of the 30,000, that would be pretty decent. So here's the link to the code, and please download it, check it out. I'm on Twitter. A lot of people bug me on Twitter when they feel free to hit me up and give me a review. Let me know if you tried it out, if it works for you, if it doesn't work. All of the above. And I think, that's all I got. So, all right, thanks a lot, guys. I'll take questions for a little bit here, and we can also take them offline later.
Calculating out some of those errors, or did you try slightly different approaches?
So the question was, I have some errors or some false positives in error detection, and the question was, what's my current approach? Is it making the error detection better, or other methods to make it better? I actually don't have any. I don't have any current funding for right now. So really my hope is to get this data set built, and then to kind of loop back to LFA, and then try to run it, run it on that data set, try out more things. But so hopefully once I have that data set, it'll be easy to run. Right now I can only sort of run it on 5 things, and it's not a very good representative sample, but if I can run it on 4,000 things, then I can pretty easily tweak different things, and if that makes it better across 4,000 things, then that's probably a good indication that that tweak is actually better. So that's sort of my that's my thought process right now. Anybody else? I know I'm standing between you and lunch. Question from the little guy in the back. Yeah, we can go, buddy. I'm hungry too. Yeah, we need to get some lunch here. All right, thank you guys.